Vitamin A deficiency is the leading cause of preventable blindness in kids worldwide. Fortifying foods is one solution, but things like heat, UV, moisture and prolonged cooking can degrade added vitamins and minerals so they can no longer help. But this week, scientists in the US announced the creation of a soluble polymer capsule that can be wrapped around micronutrient molecules to shield them and prevent degradation. It only breaks down and releases its cargo when it comes into contact with stomach acid. Katie Haler heard how it works from creator Anna Jaclenek.
In storage, vitamin A can degrade from UV light, it can oxidize, and of course moisture and heat can also help degrade the molecule. And if it's stored in a food, it can interact with different things in the food, which could potentially accelerate this degradation. Our idea was to encapsulate it, sort of shield the molecule from UV light, from other things that it's stored with. And then similarly, while it's cooking, it can be shielded from the other cooking ingredients.
Chemically, what is this encapsulation material? Because it's having to do quite a few jobs at the same time.
Yes, the material we're using is a polymer that is solid when it's in water, but when it gets to really low pH, it will dissolve and become fully soluble. And so we use this material to form a physical barrier about the micronutrient. In some cases, it can actually form certain interactions with the micronutrient to make a very stable encapsulation.
If it's solid in water, in pH neutral conditions, and then it becomes liquid or dissolves in high acid conditions, those are what you would have in the stomach, right?
Correct. Part of it is the properties of the polymer. It's able to repel water because of this sort of physical barrier. If you imagine it's a matrix structure, so it's sort of a solid wooden ball, if you will, and throughout it is the micronutrient.
How well does it work? What did your tests reveal about this?
When we do a boiling test for 2 hours, if it's not encapsulated, vitamin A is completely degraded in that amount of time, whereas the encapsulated vitamin A in our material is able to maintain its stability for those 2 hours and even longer.
So how does this affect how much of these micronutrients are actually absorbed?
In humans, we used iron as the micronutrient to study its ability not just to be absorbed by the body, but actually to be incorporated into the red blood cells, which is an indication of bioavailability. And we were able to show that basically our encapsulated product, which is very stable and prevents interactions in the case of iron with other foods, is able to release in the stomach and be absorbed by the body equivalently to iron that's not encapsulated.
Is there a danger of interaction with other food substances or medicines that someone might be taking?
Yeah, that's a very good point. I think one of the reasons that we did this type of encapsulation is that we wanted to prevent interaction of the micronutrient, for example, iron, with other foods. We have not specifically tested interactions with medicines, but we would think that it does not interact.
I guess one of the next steps is to actually get this into the industrial food chain, right? So do you know how much it's likely to cost?
Difficult to estimate the cost at this early point. I know there have been some cost analyses done on fortifying different foods like bouillon, which is highly consumed in some of the areas where there is a lot of micronutrient deficiency. And in that example, adding the amount of daily recommended intake of a certain micronutrient like vitamin A would change the cost of that bouillon less than 1%.
Because I guess it would need to be cheaper than the cost of supplements, right, to make it worthwhile doing.
Sure. Our bigger vision is in collaboration with the Gates Foundation would be to partner with people who already produce the maize flour or the bouillon. And so the micronutrients would be added to these products wherever the products are already made. And then the transportation aspect would be essentially equivalent to what it is now for those particular foods, because that allows the transportation part to stay exactly as it is. There's no added infrastructure.
Sounds very promising. Anna Jaclenek, she's at MIT, and the paper she was telling Katie about has just come out in the journal Science Translational Medicine.